So we're going to do a little bit more complicated Lewis structure problem. So we're told to draw the Lewis structure in all of its resonance forms for the chlorate ion, ClO3. So the first thing that we want to do is we want to figure out the total number of valence electrons contributed by this molecule. Okay, so we have chlorine. Chlorine has 7 valence electrons. There's only one chlorine atom, so that gives me 7 valence electrons. We also have the element oxygen in this molecule. We know oxygen has 6 valence electrons. There are 3 oxygen atoms, right there, 3 oxygen atoms. So that gives me 18 valence electrons. But then we have a charge, right, the -1 charge. So we're going to add 1 electron. We're going to add these up. This is going to give me 26 total valence electrons contributed by this molecule. On a side note, if I were to have a positive charge, I would have subtracted electrons. And you always need to take into account the magnitude. So in this case, we had a -1 charge, so we added 1 electron. If the ion had a -2 charge, we would have added 2 electrons. So now we need to draw a skeletal structure for this ion, for this Lewis structure. So what we have here is a single chlorine atom and 3 oxygen atoms. Remember that one of the rules tells us that the least electronegative atom goes in the center. So chlorine would be the least electronegative atom, and so that would go in the center. But another way you can think about it is there are 3 oxygen atoms and only 1 chlorine atom. So the oxygen atoms should be the terminal atoms. So we connect all the atoms together with a single bond, and then we use whatever electrons are left over. Remember, we started with 26. There's 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons in a single bond. So that's 6, so we have 20 electrons remaining. Okay? We can put electrons around the oxygen atoms. Remember that any electrons left over, we want to put those on the terminal atoms. Okay? So now let's count it up. We have 8, 16, 24. We started with 26 electrons. Minus 24 electrons gives us 2 electrons left over. Those electrons are going to be put on the central atom. Okay? Don't forget that you need your brackets with a charge whenever you have a charged species. So there's my -1. Well, this is the simplest resonance form of this molecule. It's not the best resonance form. It's just the simplest one to get to. Remember in the lecture PowerPoints we were talking about formal charge, and formal charge allows us to be able to distinguish which structure is going to be the best if there's many different ways that we can draw the structure. Okay, so we're going to look at other ways that we can draw this structure here. So what we could do is we could shift 2 electrons from the oxygen atom, take those 2 electrons, shift it here, and we would get a double bond. 2 of those electrons were moved, so we only have 4 electrons. We still have electrons here, and we still had electrons here. Let me take a step back. We said we need to look at formal charge, right? So I should look at the formal charge on each one of these atoms to see if it is a good Lewis structure. Remember that we want to minimize the charged atoms, right, with this formal charge. If we do have to have atoms with negative or positive charges, we want to minimize that magnitude. But if we can get it all to formal charge of 0, that's what we want to do. Okay, so how do we get formal charge? Remember, so let's look at each one of these oxygen atoms. All these oxygen atoms are equivalent right now. So for oxygen, we would say we take the total number of electrons that it should have if it was unbound, right? If it was a free atom. So where do we get that from? That's just the number of valence electrons on the periodic table. So that's 6. And then we subtract the number of lone pairs you get each of those electrons. So 2 per lone pair, plus 1/2 the bonding electron. So there's a single bond there. So you get half of those electrons. That's 1 electron. You get all of these lone pairs. So each one of these electrons. So 1, 2, 3, 4, 5, 6, plus the one in the bond. So you would get 7. So that would give you a formal charge of -1. Okay, so you have a formal charge. Here, let me change my pointer color. This will make it a little easier to see. All right, so we'd have a formal charge of -1. All of these are equivalent. Okay, -1, -1, -1. Switch back. So what about the chlorine? So chlorine has 7 electrons from the periodic table if it was a free atom. Now let's see what electrons you have for this chlorine atom. Remember that you get all the lone pair electrons. So you get 2 plus 1/2 times the number of bonded electrons. So you have 1, 2, 3 single bonds. Each one of those, right? So we can do this. So we said there were 2 electrons from the lone pair plus 1/2 times the number of bonding electrons. So there's 2 here, 2 here, 2 here. So that's 1/2 times 6, right? So that would be 3 plus 2 would give me 5. 7 minus 5 would give me 2. All right, so this would be a positive. I'm not going to change the color again. That would give me a positive 2. So we want to see if we can make these all 0 formal charges. If we can, that's great, but we want to at least minimize them, right? So we have a positive 2 charge on a somewhat electronegative element. We don't want to see that. Okay, so again, we can shift these electrons here. We did a double bond. So let's look at this. Don't forget your brackets, and don't forget the lone pair here on the chlorine. Okay, so let's look at this oxygen. Now this oxygen different than these 2 oxygens. So let's do the formal charge. Again, oxygen 6 minus the number of non-bonded electrons, right? So 1, 2, 3, 4 minus 4 plus 1/2 times the number of bonded electrons. So you have a double bond here. That's 2 plus 2 gives me 4. So we have 4 plus 2 would give me 6. That gives me a formal charge of 0. So we're doing better here. We're doing better on that oxygen. You have a negative, you have 0 formal charge. This oxygen has not changed. This oxygen has not changed. It's still a -1, still a -1. Now let's look at the chlorine. So the chlorine is going to be still 7 minus 1, 2, and then half of the bonding electrons. So 1 here, 1 here, 1 here, 1 here. So that's 4, 5, 6, 7 minus 6 gives me a +1. Okay? When we shifted these electrons up here, it would have been just as easy for us to shift these electrons. Okay? So there's actually another resonance form. Okay? We have Cl. Oh, you could have put that double bond here. Okay. Still need the brackets. Okay. So now we would have a -1 formal charge here. That would be a 0. That would be a -1. and that's still a positive 1. Same thing. We could have drawn it a little bit different, right? So we could have had the double bond on this oxygen instead. So we still have the chlorine. Okay, single bond. This would be a single bond. And this is where the double bond could have gone. Okay? Still need my brackets. So this would still be a positive 1. This would be a 0 formal charge. This would be a negative 1. This would be a negative 1. Okay, so now we have gotten the chlorine to a positive 1. We can get it to a formal charge of 0 if we were to shift another pair of electrons. Okay, so we can have yet again another set of resonance forms. Okay, so let's draw it here. So we have that double bond here. There's 1, 2, 3, 4 lone pairs. We could have made this the next double bond. 1, 2, 3, 4 lone pairs of electrons, and this is still a single bond, oxygen. 1, 2, 3, 4, 5, 6 electrons. We still need the brackets. Negative 1. Okay, we already know what the formal charge looks like on this oxygen. That's a 0. That's a 0. Oh, I forgot my lone pairs. Try not to do that. Try not to forget your lone pairs on the central atom. It's easy to do. If you were to do it on an assignment, you would get points taken off. So we've already seen an oxygen like this, right? Seen an oxygen like this. Remember, formal charge is the number of valence electrons minus the total number of lone pair electrons minus 1/2 of the bonding electrons. So oxygen 6 minus 1, 2, 3, 4, 5, 6, and then half would be 7. 6 minus 7 would give me negative 1. Okay? So that's yet another form, resonance form. But we could have put that second double bond somewhere else. So we still have this chlorine. Okay? We could have this double bond here. We could have the double bond here, and this would make a single bond. So we would have 1, 2, 3, 4 valence electrons. 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4. Okay? So what is the formal charge on the chlorine? Okay? It would have been 7 minus half of the bonding electrons. So here's a bond with 2. So you count 1, 2, 3, 4, 5, and you get all the non-bonding electrons. 6, 7. 7 minus 7 gives me 0. Okay, so we got that formal charge to 0. Same thing here on the chlorine. They're equivalent, right? 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. Formal charge on this oxygen, we've already seen an oxygen like that. That's negative 1. We've already seen that type of oxygen. That's 0. That's 0. All right? But we could have drawn it another way. We could have put chlorine in the center. Then we would have had double bond, single bond. Okay, double bond, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. So this is still a 0. 0 formal charge, 0 formal charge, negative 1 formal charge. Now the formal charge must add up to the overall charge, right? So each one of these resonance forms, the formal charge inside of the bracket should add up to the actual charge of the molecule. So it does here as well, right? So here's a 0, here's a positive 1, negative 1, negative 1. That would give me a negative 1. Okay, so what we would say about these resonance structures, there are 7 total resonance structures, resonance forms. So we would call this a minor structure, and this would be the second set here would just be a minor resonance form. Each one of these would be a minor resonance form, and then each one of these would be a major resonance form. Okay, like I said earlier, this is a somewhat more complicated problem, but you should be able to do this. The expectation is that you should be able to draw all of the resonance forms for molecules that have resonance, and you should be able to use the formal charge in order to figure out what is the best Lewis structure possible. So this major Lewis resonance form here, this would be the best possible resonance structure for this molecule, and each one of these is equivalent. They're each resonance forms. Okay, so you should be able to do this.